Yeah, great. So everyone, thank you for attending and thank you for your time. This is the start of a new chapter in our Automotive Ethernet book. For those that don't know, Intrepid Control Systems, we publish a book, goes back to 2015, but we're on our second edition. And until now, we haven't had a lot of cybersecurity information inside of it, but cybersecurity is certainly a big topic, especially as we move forward with software-defined vehicles and new zonal architecture. So this presentation is the first attempt at creating some content around automotive-specific cybersecurity, and more specifically around the future for the automotive industry for most OEMs at least, which is software-defined vehicles. Again, my name is Colt Correa, and welcome to connect with me on LinkedIn. Here's the LinkedIn link. And with that, I just want to say, if you have questions, please put them in the Q&A. And if anybody can help me, Jordan, if you're going to be listening in, sometimes it's hard for me to see the questions as they come in because I'm involved in the presentation. So if you can message me or speak up if there's questions, I certainly would welcome questions as they come in as we go through.
No problem.
Okay, so cybersecurity. So introduction, vehicle hacking sort of is really not new. There's been a lot of motivations since the start of the industry from a mechanical standpoint, just to improve vehicles. We see, a lot of enthusiasts with aftermarket products, from stereo, audio systems to improving performance on engines and so forth. So it's really not a new thing. It's been around since before even electronics was a big part of the auto industry, and of course hacking includes malicious theft as well. But what is new is modern vehicle hacking is more developing to be, as expected, more and more electronic. It's been happening for a long time in the industry, and there's certainly more to hack in a modern vehicle, and there's even stronger motivations as cars become connected, in the sense that there's a possibility that multiple cars can be hacked at one time. So we do see that the hacking industry for automotive specific related malicious things that happen in the industry are, is on the rise, and we see this continuing as software becomes more and more part of the vehicle, and vehicles become more and more connected to the internet. So this is really driving a lot of the fear and scare of what's happening. Of course, most people in the industry know about 2015. There was a group of guys that hacked a vehicle remotely and was able to show that they could do things with the vehicle remotely. So this is the ultimate threat, remote hacking. Many vehicles while on the road would be the ultimate doomsday scenario. And the 2015 hack was showing that this is not just theory. Although there is, of course, with the news, there's a lot of scare tactics in the news saying, we can remotely control your vehicle. The reality is with the vehicle, like all vehicles that I'm aware of, it had safety measures in place where the hack really could not have been dangerous. You could not have done this while the vehicle was on the road, but they did show that they were able to disable some features, and while the vehicle was under 5 miles per hour, control, and get the vehicle to do bad things while the driver was trying to stop certain things from happening. So that is definitely scary for the lay person, and cloud-based hacking definitely is a threat, and especially because of, as I mentioned, all the connectivity. And SDV vehicles, one of the big things that is happening is more and more connectivity for vehicles to the internet, and this leads to the possibility of more and more potential threats.
We got a comment saying that is patently false. Do we know what that means?
And I'm not sure what is patently false, but
the researchers were able to have full control of the vehicle at highway speeds.
Not this Jeep one. No, that's not true.
Okay.
It only happened in the parking lot. So we can argue that point later, but we won't argue it around now. So let's go into SDV architecture a little bit. How is it different than traditional architectures? So traditional architecture of a vehicle is what's called domain architecture, where you have multiple domains, multiple multiple domains that take care of a particular function of the vehicle. Like, for example, powertrain domain, braking domain, HVAC, lighting, cooling. There's lots of different domains. And over time, each one of the domains has developed its own sort of network, or you might have multiple networks, one for HVAC, one for the lighting in the vehicle, braking, powertrain, so forth, as I mentioned. So this is a traditional architecture where you have electronics and ECUs and networks dedicated for a particular function in the vehicle. And what's happened is the electronic content has grown so much that we see even hundreds of ECUs in the vehicle, and there's a motivation in the industry to reduce the hardware complexity in the vehicle. In other words, reduce the number of ECUs, reduce the number of networks, reduce the complexity of the wiring harness. And one way to do that would be to move towards a different type of architecture, and that would be zonal architecture. So in a zonal architecture, the ECUs, or the electronics in the vehicle, the actuators and sensors, are grouped together on a network, not based on their function in the vehicle, but more so based on their location in the vehicle. So, and second aspect of this is that the electronic control units that used to be in a domain architecture become essentially sort of dumb actuators and sensors that are remotely controlled. And we put most of the control into a central processing unit. So this is sort of the architecture that supports SDV the best. So there are many OEMs driving towards this architecture, and the zonal architecture not only supports a simplified hardware architecture, but also supports software-defined vehicle well, in addition, because we have a central processing unit that does more and more and has more and more control over the entire vehicle. So you can think of a zonal architecture as essentially what used to be in the past hundreds of different ECUs around the vehicle. And as much as possible, we're taking that functionality and putting it into the we're putting it into the central processing unit. So this central processing unit certainly will be a key aspect of all the software functions in the vehicle, but also a central spot where future hackers are going to look towards, trying to crack it. And I will say that most most zonal architectures from all OEMs, in fact, all OEMs that I'm aware of, keep the safety critical systems like ADAS, braking, and even powertrain separate, because it's just too much of a change. It's too risky to put all of the systems onto the same network and controlled by the same ECU. So it is important to say that OEMs, from a security standpoint, do architect the hardware itself to prevent some hacking, and this is one of those measures where the sophisticated high bandwidth systems that are vulnerable stay like they are today, so that we don't expose those safety critical systems to possibility of hacking. So we don't have time to go into all the enabling technologies of the SDV vehicle, but what's important to understand is, and by way of introduction, is that the SDV, or zonal architecture, this is another way to look at it, and from a schematic standpoint, is going to be supported by Ethernet technology. So the backbone of the communication between all of the different zones in the vehicle is always Ethernet. I've never seen architecture that is not based on Ethernet. And that, when I say Ethernet, I mean automotive Ethernet. And automotive Ethernet had speed rates all the way down at 10 megabits per second, all the way up to what will be coming in the future at 25 gigabits per second. We have 10 gigabit per second available now. And there's many different protocols that exist on top of Ethernet that enables this type of architecture as well, including GPTP, time synchronization, tunneling for transport layer, IEEE 1722 for transport of data across the network. Could be audio video data, could be CAN/LIN legacy network data. There's also time-sensitive networking protocols that are employed for real-time control. The important thing to understand here is that Ethernet is used as the backbone, but in the automotive world, that's different than the world outside of automotive, generally speaking, is that we're using a lot of protocols that are not based on internet protocol, not IP-based protocols. Therefore, some of the cybersecurity techniques that we need to employ to protect the network don't fit exactly to what's traditionally done outside of the automotive world. So outside of the automotive world, cybersecurity is a huge topic as well. There's lots of hacking that's being done. But in the internet, the protocols that are used in the internet are all IP-based, internet protocol-based. And in automotive, one big difference is that we do use protocol. We do use internet protocols, don't get me wrong. But in addition to internet-based protocols, we also use real-time protocols as well. So we have to be mindful of that. That's one of the big differences between SDV cybersecurity and general cybersecurity outside of the automotive world. So in summary, relative to zonal or SDV architectures, cybersecurity implications is that as a result of the software becoming more powerful in SDV, becomes more dangerous as well, even more so than what we see with current vehicles. And centralized computing will put more attention of attackers on a single device. That's the central compute module. That's where most of the decisions for a lot of the functions of the vehicle will be made. And therefore, that will be sort of the focus of attacks. And remote control over a network will be more common in SDV vehicles. As I mentioned, the central brain or central compute module will remotely control most the actuators in the vehicle of the future. And this leads to more vulnerabilities from the network standpoint itself. Rather than having all functionality inside of an ECU, we're going to be seeing functionality being controlled over the network. And therefore, the network in the future, it's more important to have security and capabilities so that we prevent attacks. Okay, so let's talk about when we talk about cybersecurity, one of the most important things to understand well is what are the attack vectors or surfaces that can be that are vulnerable to hackers. And as I mentioned before, hacking a vehicle is not new. So there's been many different types of physical or mechanical hacks that have been done over time, even before the vehicles were electrified and electronic control. But in the electrical world, it seems like it's scarier because of several reasons, because electronics is not as well understood as mechanics, number one. And then secondly, and probably more importantly, is that, as I mentioned, vehicles become more and more connected to the cloud. And this opens up, the possibility that multiple vehicles in one time can be hacked, which is a real possibility. And I've been involved in several communities that do vehicle hacking for good purposes, to test vehicles' vulnerabilities and test auto companies' vulnerabilities. And most of the attacks that people are looking at, or most of the threats, actually is not directly related to the vehicle networks themselves. Most of it is the connectivity to external devices. So this should be a big focus. And another thing, especially as SDV vehicles become more common, one aspect of SDV vehicles is that you're going to see more software updates through the cloud, for example, and more things like remote control through your cell phone. So you see most vehicles now, in modern vehicles, you can get an app for the phone or app or website. You can unlock your vehicle. You can remote start it and things like this. And what that means is that the user accounts and login information and the methods used in the cloud become huge attack surfaces. So I've seen in the community of hackers that most of, or a lot of their efforts, I would say, I don't want to say most, but a lot of their efforts are focused not so much on on the vehicle itself, but rather the user account, login information, and the automotive company's website and infrastructure that enables connectivity to the vehicle. So you can imagine if you can perform a hack on a server at a large OEM and get into multiple vehicles accounts, then you could potentially, for example, remotely unlock vehicles or start them and so forth. So that is one of the big threats as we move forward, especially in the SDV world. Okay, sorry about that. So as I mentioned, this is just a emphasis on what I just said. As we move forward with SDV, the authentication process, the logins, the account information on servers become more and more dangerous to have. And that also, that doesn't minimize the threats also, though, to the connection points that are throughout the vehicle that connect to the outside world. That would be anything that's Wi-Fi, Bluetooth, Ethernet, or the OBD connector. These things are all still vulnerable. Okay. And as I mentioned, we're going to be seeing more and more Ethernet in vehicles as we move forward. It is the backbone for most SDV vehicles, or all SDV vehicles that I'm aware of. And Ethernet is extremely flexible and very fast from a bandwidth standpoint. There's lots of reasons why Ethernet is being used. But on top of Ethernet, one of the downsides is that everything on Ethernet is or most protocols on Ethernet are defined in the OSI model, meaning there's different layers of functionality that combine to create the functionality of the network. And the bad news with this is that the layers are intended to work independent of each other, and that's a good thing because it leads to flexibility and so forth. But consequently, it means that each layer is its own attack surface that independent of other attack surfaces. So, for example, the example I like to give is, let's say that you have perfect protection on layer 1, layer 2, layer 3, layer 4. All of these layers are perfectly protected. And then a hacker is able to download a software application into your ECU and make that software application run. So if that happens, then all the layers of security, especially on the network that we're going to be talking about, like MACsec and SecOC, other technologies, are not going to do anything for you, because the software that's the invalid or bad software that's running, malicious software that's running inside the ECU, if it's running inside the ECU is going to treat it like a valid piece of software. And any data that it generates, it's just going to go right down through the stack as if it's good data, and no amount of protection at the lower layers is going to protect a malicious software that's up on the higher layer. So that's one of the key important things to understand about cybersecurity, is that these layers are independent, and you have to protect all of the possible threats to all of the possible layers, unfortunately, in order to have a secure system. Okay, so let's go through some of the cybersecurity basics. Again, this is going to be with an automotive focus. So cybersecurity is a huge world, and there's lots of things that are different in the automotive world, specifically because outside of automotive, we have sort of interactive. A lot of the cybersecurity is designed assuming that a human is interacting with software on one end of the system. And in the automotive world, a lot of what we do is embedded control, meaning it's sort of hands off. So there are some differences, and we'll try to cover those as we go through the slides. So first thing is, with cybersecurity, there's often, we hear the term Cypher Suite, and Cypher Suite is just a specific agreed upon set of algorithms and protocols and methods that are used to attain secure communication. And we define these cyber suites because we have ECUs or computers that need to talk to other computers, not necessarily from the same manufacturer, or that are different from each other. So there has to be some agreed upon set of methods and algorithms in order for the two or more ECUs to communicate with each other. And there's generally, this is broken down in the 4 different categories. One is authentication, and this is unfortunately often used differently in the automotive world than it is outside of the automotive world. And outside the automotive world, authentication just means that the user of the client, or the user of the system that is the client, is actually a valid and good user, a good person, or a good computer. And that's also valid for automotive world, but the difference is that the authentication outside the automotive world is often used to verify human identity rather than electronic identity, or a valid embedded controller, for example. And in the automotive world, a lot of what we do, as I mentioned, is embedded, which means hands-off, users not directly interacting with the controller or computer. And the way that we often use authentication in the automotive world is meaning authentication of messages in the automotive networking system. So authentication of messages within the within a networking system just means that it's a method to ensure that the transmitter of all messages, or the transmitters of all the messages on the network, are valid and good transmitters, and that we don't have a bad transmitter that's transmitting malicious information. That's generally the way we use authentication in the automotive world, as opposed to outside automotive. Authentication just generally applies to the user, human user of the system. Then we have a key exchange. This is used to distribute keys between the talkers and listeners of a system. In generic internet algorithms, often there are only 2 participants, and this can be some trouble for the automotive world, because in the automotive world, there's often 1 talker and many listeners. And we see that with legacy network systems like CAN, LIN, FlexRay. There's at any one time 1 transmitter and multiple listeners. And even in the Ethernet world now, we have 10BASE-T1S, which is a bus or multi-drop topology, where we have the same type of issue, where you have 1 talker and multiple listeners. So as far as key exchange goes, this is something that we're actively working on in the automotive industry. We have this key exchange working for a lot of point-to-point Ethernet networks, specifically supporting MACsec key agreement that's been modified. We'll talk some details about that at the end of this presentation. That's been modified for the automotive industry. Hashing is an algorithm that takes plain text or data information and reduces it to a fixed size number, so that number can be used to verify that the data is valid and not been modified since it's been transmitted. And then encryption or bulk encryption are algorithms used to efficiently modify a large amount of data so that it cannot be understood, so that the data is not understood by an unauthorized observer. So these are the 4 main categories of the question is PSK. PSK here stands for pre-shared key. So in the automotive world, there's, and we're going to talk about this. So PSK, I see that I'm trying to answer a question that's in the chat here. PSK stands for pre-shared key. It just means that we store the keys into the ECUs in a secured manner before use. And a lot of automotive cybersecurity simply uses one of the simplest methods of key exchange. That means a pre-shared key. In other words, the key has been stored inside of the vehicle or ECU at manufacturer, or when the ECU was manufactured. Another note is there's really 2 types of encryption methods, symmetric and asymmetric. Asymmetric encryption is typically used for authentication for websites, like when we authenticate ourselves in a website, asymmetric encryption is used. Asymmetric encryption uses a public and private key. Private key is never shared by anybody. It needs to be stored, and the public key can be shared publicly. And the public key is used for encryption. So, for example, a server can send a public key to anybody, and that person can use the public key to encrypt data, send it to the server, and the server, only the person with the private key can then unencrypt that data or interpret the data. So that's a private public key asymmetric encryption. That's used for a lot of authentication methods like TLS, transport layer security. In the old days, it used to be called SSL, secure socket layer. That's used to as part of the authentication process. The downside of the asymmetric encryption is that it uses a heavy amount of processing power. So it's not really suited for bulk encryption of data across the network. So in that case, in the automotive world, most of the encryption that we're talking about or authentication that we're talking about, we're going to be using symmetric methods, meaning symmetric keys. And symmetric meaning the same key is used for encryption as decryption. Okay, so automotive network security, it's been around for a while. SecOC is specifically something defined within AutoZAR. This goes and supports many different legacy networks, can be used. It's sort of a generic security method that can be used for nearly any type of network, including legacy networks like CAN, LIN, FlexRay. So we're going to see this still being used in the future, even with SDV vehicles, because it's the type of security that supports legacy networks. And the processing overhead is on a per message basis. So what this means is that in SecOC, you have to choose which messages you want to secure and which ones you don't want to secure. And with all of these methods, authentication of data is necessary, and encryption of the data is optional. So we see most data that's secured on an automotive network is just secured in the sense that we want to secure or authenticate it, meaning that we know the transmitter of the data is a good and valid transmitter. We're not as interested in encryption, although of course encryption is necessary for some types of things. So if you're transmitting over an automotive network, personal information, that's something you're going to want to encrypt. For example, any keys transmitted over a network, that's something you're going to want to encrypt so that people can't interpret the data. But in general, a lot of the control data of a vehicle, like engine speed or vehicle speed, these types of things, it really doesn't serve any purpose to encrypt the data because you can get that information other means, and it just encrypting the data causes more difficulty in developing the vehicle, testing the vehicle, and additionally, whenever you say encryption or authentication for that matter, especially in real time, there is a penalty to be paid. It's not free, and the penalty is complexity. It uses more energy, there's always a delay added with any type of encryption method. There's always types of sort of latency cost. So doing cybersecurity isn't free. There is some cost associated. So we want to balance the protection with the cost of the protection. And when we move into Ethernet, there are really two main types of security that we're going to employ heavily in the automotive world. One is TLS and DTLS. This is end-to-end encryption. It only works on TCP and UDP only, though. It only works on IP protocols, but this is the method that's used for banking transactions. For when you go HTTPS, this is the security behind HTTPS, and any type of sensitive information that you provide over the network, your personal information, all this is protected on TLS and DTLS. And we're going to see this be necessary for the automotive world whenever the automobile needs to connect to the internet in any way and share sensitive information. So this is certainly going to be protocols that are going to be used heavily and are used now. as we move forward. I did see a question just pop up that is SecOC only authentication, or does it also provide data confidentiality as well? So the SecOC in practice is used mostly just for authentication. That is to verify that the transmitter data is valid and that the data is valid. However, SecOC does have the option to also encrypt the data as well. But the encryption of data is just not that common with SecOC. So hopefully it answers the question.
We had one more question, Colt, as well.
Okay.
Could you say something more about the key exchange methods, protocols, solutions used by OEMs? Is there any common approach here, or perhaps each OEM has its own approach for that?
The key exchange over the network itself is defined by standards that we're going to cover if I have time. This presentation is quite long, but so for example, in TLS and DTLS, part of that protocol is the key exchange. So you have to define within these protocols how we're going to exchange keys. And when we talk about MACsec, which is going to be the main network security used in automotive SDV vehicles for Ethernet protection, there's also a automotive industry standard that's being worked on called, it's a MACsec key agreement. It's an IEEE standard. It's been in the industry for a long time, just like MACsec. It's not new. It's been around for a long time, but the automotive industry is sort of adapting the technology for the automotive use. So there is an automotive MACsec key agreement that's being worked on through Open Alliance TC17, and anybody's able to join that for free and to get those documents and participate if you want to. But that's now being developed and will be coming out shortly for point-to-point communication, and then bus-based or multi-drop communication, something that we're going to be working on in the future. So really, in the future, we see SecOC being used for legacy networks, TLS, DTLS used for any type of communication outside the vehicle, or any type of encryption within the vehicle, like sharing files within the vehicle, or one ECU flashing new software into another ECU. We can use TLS, DTLS to do these transfers. And then MACsec is going to be used as an overall protection point-to-point on Ethernet networks. I do have IPsec here. IPsec is something that has been a topic in the past, but we see this topic waning, sort of. It's going away because IPsec has the downside that it only protects internet IP traffic. And so IP, as I mentioned before, IP traffic is not exclusively the only type of traffic that exists on top of an automotive Ethernet network. So MACsec protects at a lower level than IPsec. So if you're using MACsec, then IPsec is in some ways, you make an argument that it's somewhat redundant. There's different types of protection and communication too that's important to understand. And this is where we really see the difference of TLS, DTLS. TLS and DTLS is sometimes referred to as end-to-end or app-to-app communication. This means that once you have keys between two different applications within two different electronic control units in the vehicle, they can communicate through a secure channel that's secure through all the layers that go up and down through both ECUs. So that's the advantage of TLS, is that we're protecting the data at the source of where the data is generated within the application. So app-to-app protection is really good protection, it's end-to-end protection. But the downside of this is that you can imagine that there's many applications, there's many sources of data within a single ECU, and there's many sources of data and many sinks of data. So there's lots of sources and sinks. And as soon as you start adding multiple sources and sinks, each channel, each connection, each one app to another application needs its own key. So then it quickly becomes very complicated and unmanageable from a lot of different aspects to do point to or end-to-end protection for every type of communication that's happening. It's just not practical to implement because of the number of keys that would be required and the number of communication overhead that would be required would be too complicated. Therefore, the industry has moved towards something that is point-to-point automotive MACsec. Now, it's important for me to say automotive MACsec because in the automotive MACsec world, it's designed or the practice of it, the application of it is point-to-point. And we'll talk more about that in a minute. But so MACsec itself, in a general sense, the IEEE standard does support end-to-end protection, but in the automotive world, it's just not the way that we implement it. We're implementing it more point-to-point, and point-to-point means we're just protecting the port. It's all, even the spec, it says port-based protection. So that's exactly what we're doing in the automotive world. We're protecting one port to another port. But the downside there is that each port-to-port connection, each point-to-point connection does require its own key, and there needs to be some way to distribute these keys throughout the vehicle. We'll talk about that with MKA in a minute.
Couple more questions just came in.
Okay.
What are the example of different types messages used in automotive Ethernet, which are processed on TCP, UDP, IP, TLS, HTTPS?
Yeah, so the internet protocols, the IP, all of the IP ones, TCP. Well, let me step back. So minimum TCP, we see TCP is generally speaking not used for real-time control. So it's not used for like embedded control like we would normally see in the automotive industry. UDP is just a datagram. It's like fire and forget. So that type of communication, we do see like control data. So for perfect example is there's a very popular protocol out there, some IP for middleware within the automotive industry, and that runs on top of UDP. So we do see some UDP Ethernet communications on top of IP that is used for real-time control. And generally speaking, though, that real-time control is not necessary for secure communication. But if you're sending a message on some IP, for example, to unlock the doors, that you could use DTLS to secure that information, for example, if you wanted to. So we see there is some level of sensitive information that is transferred on top of UDP. And when we go to TCP, TCP is typically used for file transfers, reflashing, software download. So the big difference between UDP is just a datagram, fire and forget, and which is good for real-time control. And TCP guarantees the delivery of all the data to from the source to the destination, or at least the destination knows if the data doesn't arrive correctly. So TCP guarantees the delivery of data, but it's not really good for real-time control. So therefore, TCP is used for things like file transfer protocol, software download, these types of things. And most communication outside the vehicle to a server is also TCP. So when we look at HTTPS, that's on top of TCP. That's HTTPS is just a protocol on top of TCP that uses TLS as its security. And so that's the most common, one of the most common types of protocols used. And that's still going to be used between the vehicle and server communication for anything that happens, vehicle to server type of communication. So hopefully that answers the question. And in addition to that, there are protocols like TSN that are not at all related to IP, that need to be protected too. And that's the reason why MACsec is proposed, because MACsec works at layer 2. It works below all of the communication that happens on top of Ethernet and provides some good overall protection.
Okay, and then two more just came in. How do the non-IP protocols map to Ethernet? I know much of the CAN-based protocols have been mapped to UDP IP, but I'm curious how others are making the transition.
Well, there is no transition. So when we talk about Ethernet-based TCP, Ethernet-based time-sensitive networking, TSN, those are in parallel to IP. Those provide a different function for the vehicle, and they're not going to get mapped into IP. They are in parallel to IP. They do things that IP cannot do, like, for example, time synchronization. Like, for example, guaranteed delivery with a bounded latency from a source to a destination. Those things are in TSN, not related at all to IP. The completely separate protocols, completely different type of methodology. So that's the reason why we need something that's more than just IP based for security, is because in automotive networking, we have non-IP based communication.
Okay, great. Thanks, Paul.
Yeah, and ICV, we're gonna talk about that in a minute. So let's get into just in general. I made this slide because most protocols, whether you're looking at SecOC or MACsec or even IPsec, they work with some basic principles, and these are the basic principles. So in automotive, as we mentioned, we're going to be using symmetric encryption and decryption. That means we have the same key on both sides. And so this is a secured key that has to be secured in a very good manner. And most automotive electronic ECU hardware has what's called HSM, or hardware security modules, that provide functionality, and most microcontrollers provide functionality so that keys can be written but not read. So the key storage is very important. And then we have some algorithm. AES is one of the most popular ones, advanced encryption, what is it, security, I think. I can't remember the acronym. But AES is one of the most popular types of algorithms used for encryption. And all it is it takes generally three different inputs: the data that you want to encrypt or authenticate, an initial vector, and this can be a counter, it can be a random number. It depends. It's a little complicated depending upon exactly what you're doing, but there needs to be some randomness involved in the algorithm, because that will prevent a replay attack. If you don't have any randomness, it means that all a hacker would need to do is record secured traffic and then replay that secured traffic, and it would look like good data. And the way that we can prevent that is by using an initial vector, a random number, or a counter, and all real-time secure protocols use that. So then you have the input of, as I mentioned, data. This would be plain text data that you can just see and read normally. Binary data would go into the algorithm, initial vector, or random number or counter, and the secret key. Those are the three inputs. And then with authentication, this is specifically authentication, we get what I'm referring to here is integrity check value. And I'm just using that because that's the term that's used for MACsec. The other name for it could be MAC. Unfortunately, it's not related to the MAC controller of an Ethernet. You have to watch out for this, because MAC can mean media access controller, like a normal Ethernet, but it also means, in the security world, message authentication code. So like in SecOC, unfortunately, it's called message authentication code, not to be confused with the media access control. So that's the output. And then that is transmitted with the data to the receiver. The receiver then receives this ICV value, takes the data. The receiver has to also have the information from the sender on the initial vector. Well, different protocols handle this different ways, but the randomness has to go into the algorithm, as well as the same key. And so you take these same three inputs with the same algorithm, and the receiver calculates independently its own ICV. And if these are equal, you're guaranteed to have been authenticated data. So that's kind of how authentication works on a data standpoint in automotive world, regardless of what type of security you're using. SecOC works this way, MACsec works this way, and to my knowledge, everything else generally works this way. And when we want to do data encryption, which again is not as common, especially for real-time control communication, it is used for software download, for reflashing, that type of thing, sending passwords, sending user information across the network. But generally speaking, data encryption is not something that we use for real-time control. But it's the same thing, the same inputs. Would say the data is called plain text. This is what we can read. Goes into the algorithm with the initial vector key, and then these algorithms like AES then can encrypt the data, and then we just push the data into the message, which would be secure data encrypted, and then the algorithm on the receiving side then can unencrypt that data. So they're very, authentication alone and authentication with encryption are very similar to one another. Okay, so let's talk about the details of SecOC. This is directly from the AutoZAR specification, I believe, and you'll see that in SecOC we have PDUs, protocol data units. Essentially, that's the data we're talking about. It goes into the algorithm, the MAC generation. In this case, it's message authentication code. We have a counter. And the only real big difference in SecOC than our general use case is that the counter is sent along with the data, along with the MAC. So along with the MAC and the counter and the data all get sent to the receiver, and then the receiver there's some reconciliation that happens with the counter. There's some algorithms about the receiving counter, what it uses, but it uses the same counter. MAC verification, it does the same thing. It creates its own value and it compares, and if the receiver calculated value matches that of what was transmitted by the transmitter, you're guaranteed that the transmitter is a valid transmitter. So that's SecOC in a nutshell. I know we're running out of time here, so I need to move even faster than I already have been moving. TLS, DTLS is very complicated protocol. There's no way. I mean, I want to do a whole hour presentation on just TLS in the future. But essentially what happens is we have a TCP handshake that establishes communication. Then we have asymmetric encryption to validate the authentication of the user. And then there's with the asymmetric encryption, we're going to do a key exchange, and the key exchange is going to be a symmetric key so that data transfer can happen in real time. So that's symmetric encryption. At the end of the day, the data transfers over TLS or DTLS would be with symmetric encryption. Again, remember, symmetric encryption uses the same key for encrypting as decrypting, and it's much faster and easier to implement from an algorithmic standpoint than compared to asymmetric encryption. Asymmetric encryption has the advantage that you can have a private key to unencrypt data and a public key that anybody can have to encrypt the data, and that provides very secure communication. Okay, so let's get into MACsec. I only have a few minutes here, so let me just skip over to this slide. The MACsec, the way it works is, as I mentioned before, as we went through the calculation of the integrity check value and the data encryption. Essentially, we have a standard MAC frame here that destination address, source address. This is a source and destination MAC address. We have an ether type. In MACsec, we have a reserved ether type. So a MACsec frame coming out is going to have a MACsec ether type. Then there's going to be a sec tag that contains information about the security options that are being used and other information like a packet number. And then we'll have the original ether type. Secure data this could be plain text, it could be unsecure or secure data, because encryption, again, with MACsec is optional. You don't have to use encryption, so you can use, the data can be transferred plain text so everyone can see the data if you want to, or optionally can be encrypted. And then we have the ICV, the integrity check value would be appended at the end. And then this is just a standard frame checksum here for part of Ethernet. So really what we're doing is we're at the cost of adding some bytes to the message. So again, there's cost. This is 100% overhead. The MACsec ether type, the sec tag, and the integrity check value are all overhead for MACsec, but this is just how we package a MACsec frame. And there's lots of different options to MACsec. Again, MACsec is another presentation I could do easily for a full hour. But there are there's lots of sources of information for MACsec as well if you're interested in going into that in detail. But this is the basic way that the frames look like on the network for MACsec. Important information about MACsec, especially for automotive, is that there are chips, PHYs, Ethernet chips from vendors like Marvell, NXP, and so forth that do this in the hardware. So MACsec itself, you can imagine if we're transmitting Ethernet frames, the integrity check value, and if we're going to do encryption, has to be done at wire speed. In other words, at the speed the network can run. So if we're talking about 10 gigabits per second Ethernet, that's a lot of processing that needs to happen. And that's more processing than what is possible to be done in a microcontroller, unless you're going to run your network at like 1% efficiency, which is not a good idea. Therefore, MACsec for the automotive world is something that's integrated and built into the hardware of the PHY itself. And so the way it works is inside of an ECU, the MCU inside of that particular node or ECU is going to be responsible for receiving keys and then configuration information about MACsec, and then putting that into the PHY. And that's done through a standard MDIO interface that is part of the PHY interface for all of the silicon vendors. And this is, this overall process is the way it works for MACsec in general for automotive. You need to have a physical chip that supports it. That's the point of this slide. Not something that you want. MACsec's not something you want to do in the microcontroller of the ECU. And mentioned MACsec and automotive, each point-to-point requires its own key. So we'll see that each port connection point-to-point will require its own key. And the way that these keys are generated is automotive MKA. MKA is MACsec key agreement. It's an IEEE standard that's been out for a long time, but it's generic in a way in which it's used. It's much more generic and configurable, and the automotive industry through TC17 of Open Alliance has reduced the scope of MKA to be automotive MKA. That makes it simpler to implement. In other words, there's less options. And then secondly, the MKA that's generic is not well fitted in some instances for real-time communication. So another big difference between automotive and non-automotive electronic communication is that in the automotive world, typically speaking, you have the requirement that you have the ECUs completely asleep in a low power state, and then you have to get the electronic control unit and the network active, alive, and fully functional within 100 milliseconds. And so that 100 milliseconds is that general requirement of 100 milliseconds is something that outside of automotive electronics, is unheard of. You don't hear that. So MKA, as it stands outside of automotive, has timeouts and other things that would make it not work well for automotive electronics, specifically this requirement that we have everything up and running within 100 milliseconds. Okay, so the way it works is essentially to distribute the keys, generally speaking, there's going to be a microcontroller inside of a switch that you buy. Again, this is part of a hardware. So when you go to create a network for automotive, you have to make sure the switch has capabilities for this. Like, for example, most switches in automotive have inbuilt or built-in microcontroller that you can do certain things. And then you can run an MKA software stack. And the way that this works is in automotive, there's a stored key called a CAK, Connectivity Association Key. That would be stored inside of the switch or somewhere secured storage. And then when the switch boots up, it would create two other keys that then get combined together and then get sent to the port. This KEK is for key encryption key for encrypting keys as they get sent over the network. And then the ICK is the integrity check key for data communications. And that's combined into it. So secure association key, there's lots of terms here that's hard to keep in your head, and then an SAK then will get put into the PHY, into the port and used for the real-time communication. Again, this happens all when the electronics is started. And these, the reason why we're using SAKs that are dynamically generated is because it's more secure than just using a stored key. So even if this, it gets to be a lot more difficult to hack a system where you're using dynamic keys. And we see that even with TLS, DTLS, the keys are generated dynamically and then transferred over a secure channel. And so MKA works in a similar fashion. But important to understand is that there is a MKA software stack that needs to run. somewhere within the network. Someone has to be a key server. Generally speaking, that's going to be the switch, and most automotive switches have built-in microcontrollers for this, and then those would then use the protocol to distribute the keys throughout the entire network. Okay, so just to summarize, and then I'll answer any questions after that. We just got a few minutes. So cybersecurity and an SDV or zonal architecture is going to be using some very common types of security. For example, TLS, DTLS, as mentioned before, any type of connectivity outside the vehicle over Ethernet communication should be doing TLS, DTLS for whenever there's sensitive data to be transferred. And one thing that I didn't go into that I would like to go into if I had more time is just the Ethernet switch configuration itself can provide a lot of good security. So almost every automotive Ethernet switch that's out there, you can configure VLANs, you can configure MAC addresses, you can do TCAM communication to make decisions based on traffic, and you can lock out certain traffic. You can say these MAC addresses are the only MAC addresses valid for the network. Any other MAC addresses are not valid, for example. You can do that with VLANs. You can do that with IP addresses. So just the configuration of the switch itself a proper configuration of the switch itself with policing and filtering will protect, is very good protection against unwanted communication. So that alone is very good protection. I didn't cover that at all, unfortunately, because of time. And then as a basis for those companies that want to use it, the backbone of SDV vehicles is going to be Ethernet. And to protect that backbone from a point-to-point or overall protection, MACsec can be employed. That provides good protection for things like man-in-the-middle eavesdropping if you want to protect the data itself. That's a good summary of everything I wanted to talk about. The management and distribution of keys is often the most difficult part of security. So really, that's where the focus should be. In that after, so the protocols like MACsec, TLS, DTLS, these are well-proven, very secure methods that can be used to secure networks. But if your company doesn't have a secure system for distributing keys inside the vehicle, meaning at production or at the dealership, or storing the keys on a server somewhere and managing those keys for the vehicles that are out there, then you're not going to have any protection. So often the challenge for automotive OEMs is not so much in implementing all the protocols, which that in and of itself is a challenge, but the management and distribution of keys is often where the hackers, find themselves focusing on. So let's see if there's any questions. That's the end of my presentation. I'm glad I got it done in an hour. Let me see if I can read some questions. Can both MACsec and SecOC are supported at the same time on an ECU? Yes, it is supported at the same time, but you have to remember that SecOC generally is designed for legacy automotive networks like CAN, LIN, FlexRay. The MACsec is for Ethernet exclusively. So if you have MACsec on Ethernet, there's really no point to do SecOC. And if you have a legacy network, you cannot do MACsec. So that's the reason why SecOC probably will stick around into the future. Hopefully I answered that question. Let me read this other one. Regarding the statement, each connection needs a key. What is meant with connection? Is it a link? Okay, so this is, consider you want to do a tap into a link. You need a separate key for the tap. The answer is, it's a very good question. Let me go back to so each point to point, each port, each PHY to another PHY needs its own key. So if you were to put a tap or a tool like Intrepid Control Systems, this is what we sell as tools that would be a tap where you can break this link and then sniff on this network. That's kind of like a man in the middle. If the MACsec communication was authenticated only, in other words, the data is not encrypted, then you can use the tap to monitor the traffic, no problem. The tap will work for monitoring the traffic. The tap will also transfer all the traffic through such that the ECU and the switch port will still function. The ECUs and the switch won't know that there's a tap involved in there other than some added latency. However, if you wanted to transmit data with the tap, any transmitter, whether you're a tool or not a tool, means that that tool would have to participate on MACsec. So the challenge for us as a tools provider, as Intrepid Control System manufacturing taps, is that the OEMs have to insert their key into our tap in order to transmit on a MACsec network, a secured frame at least. Hopefully that answers that question. What is the main difference between MAC and MACsec? I'm not sure I understand. I'm not sure I understand, but MACsec stands for Media Access Controller Security. This is level 2 security. And this is a standard MAC frame, as I mentioned before. And then a MACsec frame adds in additional bytes with an integrity check value that you can verify that this frame was sent by a valid transmitter. And this frame, non-MACsec frame, is shorter in length, but there's no way to validate that this frame was sent by a valid transmitter. That's the difference between MACsec and non-MACsec, or just a standard MAC frame and a MACsec frame. Oh boy, the cert authorities. So another question, how are they handling PKI cert authorities, particularly with OEMs and tier 1s? That's a question I'm not really, it's out of scope of my view, security certificates and so forth. But to my knowledge, as far as security certificates to like websites, if you create a website and you want to do secure communications, you have to buy a security certificate from one of a small number of vendors and put that into your website so that you can do secure communication to any device. And that is also true. OEMs will also have to do that for the automotive, for automotive connectivity. But to my knowledge, the certification or cert authorities are no different for automotive companies versus any other company, like a banking company or internet, internet company like Google or something.
Last call for any other questions.
Okay, we really thank everyone for your time. Glad we got through it. It's like really high level. We're just a few minutes over time. Again, thank everyone for your time. You can connect with me on LinkedIn. We will provide the presentation to the participants for whom we have emails of. So if you registered, we have your email. And again, thank you very much. This is my LinkedIn if you want to connect with me, and look forward to seeing you or hearing from you in future webinars.